Hi everybody, welcome back. In this video we're going to be introducing the electric field in more detail. In the last video we gave kind of a brief outline of what it is, what we use it for, and how we can visualize it. In this video we're going to start looking into how to deal with it mathematically. So again, our kind of sources here. This is kind of a basis for commentary on the classic Knight book, the third edition of Knight's Physicists for Scientists and Engineers, which is a really good calculus-based elementary physics book. And also some sources were taken from, some info was taken from Walker, the classic Halliday-Resnick series, though now it's just down to Walker. And also various resources from my mentor Tony Wayne, and occasionally I use plots that I've generated from Desmos. So, electric field configurations. In many situations, we discussed that it's a lot more straightforward to just calculate the electric field itself than it is to use Coulomb's law to figure out the net force. Of course, in a manner of speaking, we are using Coulomb's law just in its electric field version of force per unit charge, where we don't have the quantity of charge that's being acted upon. We just leave that to be arbitrary and something that we multiply by later if somebody actually wants to figure out the force. But here we're going to be considered with the field. Now, there are three basic general charge distributions. There's an infinitely long wire, or something that is symmetric to it, an infinitely wide plane, or a bunch of them on top of each other, or a sphere. So those are the three most basic charge configurations, and many other charge distributions can be considered in terms of these. Now, we'll come back to these three basic ones when we get into the Gauss's law discussion in the next chapter, but we're going to still kind of think of these as something to compare to, because in a lot of cases these are pretty important. So, we won't use the tricks that go with calculating electric fields due to those those basic charge configurations. We won't use those tricks yet. We're going to save those again for the chapter 27 discussion. But instead, we're going to start from first principles, in other words, just adding up the electric fields due to point charges, and eventually get into continuous charge distributions in the next video. So let's go back to considering the electric field for a finite number of charges. This is going to be kind of an extension of what we got into with the Coulomb's law two-dimensional practice back in the previous video, but this will also help us to develop some intuition about how we are going to deal with this when we need to calculate the electric field due to continuous charge distributions. For example, the electric field due to a bar of charge. So let's consider three equal positive point charges that are on the y-axis. One is at the origin, and the other two are at plus or minus d. We want to calculate the electric field at any point on the x-axis, and this is an example that was taken out of our Knight textbook, but there was actually something went wrong in that example, and the final answer that they got was actually not correct. It wasn't, at least it was not generally correct. So, and that was due to a little bit of a subtle mistake that we're going to address. So here is our picture. We have these 3 point charges. So the question is, anywhere on the x-axis, what is the electric field vector? So hopefully you can see that by symmetry, the electric field should point in the positive x direction. So however we do this problem, in the end, that fact needs to be reflected in our answer. So we're just going to pick a point P anywhere on the x-axis to do this. So we have our symmetry noted, and we use the superposition principle with the electric field. Remember, the electric field of a point charge is kq over r squared, where r is the distance from the center of the point charge. And in each situation, since it's a vector, we're going to multiply the magnitude by the unit vector going from the charge to our point P. So our 1 hat is going to go down and to the right, our 2 hat is just to the right, and our 3 hat is going to go up and to the right. Now, hopefully you don't have to think too hard about figuring out what we would call R2 hat. except there's a little trick there that makes things a little subtle. So remember, whenever you need to find a unit vector, what you can do is you simply take a vector going from the point where, in this case, the charge is, to the point where we want to calculate the electric field. So if I want to calculate the unit vector pointing from charge 3 to point P, then I would find the vector going from charge 3 to P and divide by the magnitude of that vector, which is going to be the distance from charge 3 to P. So here we go. Here are the vectors from each charge to our point P. So since point P is located at the coordinate x, 0, the 0 denoting no position in the y direction, our one vector is like, okay, how would we get from charge 1 to point P? Well, we would go over x and we would go down d. So the vector going from charge 1 to P, our one vector, is xi minus dj, where I and j are the usual unit basis vectors in the x and y directions. Going from R2 to P, we just go xi. And from R3 to P, we go over x and up d, so xi plus dj. So here are our givens so far. We want to figure out the electric field at point P. And each of these charges, Q1, Q2, Q3, has the same value, just as you can see in the diagram, back in the original problem, they're just called Q. So we could just say Q1 equals Q2 equals Q3 equals Q as another given here. Now, remember a unit vector? A unit vector is, well, a vector going from point A to point B divided by the magnitude of that vector. Well, the magnitude of these are position vectors, so the magnitude of a position vector is just a distance from point A to point B, in this case, the distance from the charge in question to point P. So, since our one vector is xi minus dj, well, the Pythagorean theorem tells us the distance from charge 1 to point P is the square root of x squared plus d squared. And that's going to be the same for the distance from charge 3 to point P. So in each of those cases, R1 and R3 hat are just given by R1 vector divided by that distance, and R3 vector divided by that same distance, square root of x squared plus d squared. Now, you might wonder, well, shouldn't R2 hat just be I? Well, here's the thing, and here's where we have to be real careful. The problem said, find the electric field anywhere along the x-axis. Well, that means we could have negative values on the x-axis. So in that case, by plugging in my R2, I didn't just plug in x, I plugged in absolute value of x squared. Or sorry, the square root of x squared. Or you could just call that absolute value of x, but calculators are more friendly with square roots, so that's why I did that. So in any case, it's not just I, it's x divided by absolute value of x. In other words, if P is located on the positive x-axis, that unit vector would be plus I. If P is located on the negative x-axis, that unit vector would be minus I. So be real careful to make sure that you are taking into account all possibilities. This not taking this into account is actually why the textbook ended up obtaining an incorrect solution. Now, I want to warn people I'm not being arrogant here against the textbook author, something that I've mentioned before in other videos. This is the best textbook I have ever come across for physics at this level, period. So whenever there's a difference between my solution and for a problem and the author of the textbook, at least 80% of the time it's because I'm the one who's made the mistake. In this case, there was a mistake in the textbook, and who knows, maybe I made other mistakes in this problem, but in this particular situation with this R2 hat, this is not one of them. But yeah, just keep in mind, it's like, yeah, I'm noting the mistake here because it's a mistake that you all might be tempted to make. It's a very easy mistake to make. It's a mistake that I have made in these types of problems before. So because of that, I was a little bit keen in noticing it this particular time because I've made it so often before. Okay, so here's where we stand. And again, our Q1, Q2, and Q3 are all the same, just Q. So now, again, just plugging in. What is Q1, Q2, and Q3? Well, it's just Q. I decided to factor that out because in this case, it's all the same. Since Q1, Q2, and Q3 are the same, I factored out just a KQ. And then I did the same trick that I did before. I used the fact that I have this, each of my unit vectors is the vector over a factor of r squared. Or sorry, each of the unit vectors is the vector over just the factor of that magnitude of the vector. And I already have an r squared there, and each r is just a square root. But in this case, we have that funny thing in the middle. But in any case, r1, remember, is the square root of x squared plus d squared, which means that r1 squared is x squared plus d squared. And we need another factor of square root of x squared plus d squared, so the whole thing therefore becomes square root of becomes x squared plus d squared to the 3/2 power. And the same thing happens with the electric field due to charge 3. But the electric field due to charge 2, again, I'm being real careful to make sure that I'm taking into account the possibility that we could be dealing in with the negative x-axis. Something on the negative x-axis. In other words, if I was not being careful here, this x in the numerator right here would end up canceling out with an x in the denominator here, and I don't want that to completely happen. So sure, it cancels out with one factor of x here, but if point P is on the negative x-axis, there would still end up being there would still be a negative value there that would be left over. So it would have a negative value to an odd power, which would be fine. So that would still take into account all possibilities. In my other E field vectors, for E1 and E3, that's taken into account by the fact that the x that's left up here, it's still left up here. It never gets canceled. So if point P is on the negative x-axis, then we would end up getting negative values that would get plugged in here. So in this case, this actually does take into account all possibilities. And notice that the vertical terms cancel. The negative d in the first term cancels with the positive d in the last term, so the symmetry ended up working out. So here is the arbitrary or general solution for all possible values for where my point P could be on both the negative x-axis and the positive x-axis. And again, we already brought into consideration that possibility, like, yeah, what if it's in the negative part? Just be real careful when you're looking at that. Now, something that is very useful to do in a lot of charge configurations, and a very common problem on the AP exam, as well as a very common homework problem and a very common test problem, is to analyze the limiting behavior. When they talk about the limiting behavior, they are talking about situations where x is very close to 0 or x is very close to infinity. Well, let's, in this case, just look at what happens when x goes off toward infinity. In other words, when x goes off toward infinity, we should expect that this would appear like just 3-point charges altogether. In other words, we should expect a 3kq over r squared, that is 3kq over x squared, when x goes off toward infinity. Well, let's find out if that's what we get. So, let's take a look at this and figure out whether we can actually extract that from our general expression. Well, as x goes off toward infinity, a quick glance shows you that x squared plus d squared just goes to x squared in that limit. In other words, when x gets really, really big, d is fixed. That's the distance between the middle charge and either of the other charges. So that's fixed. So once x gets big, x squared plus d squared just goes to x squared. But you need to be really careful when you're doing those types of things, because sometimes when you make that type of approximation, everything might end up getting 0, and you're like, yay, the electric field goes off towards 0. Well, here's the thing. When they're talking about limiting behavior, nothing is ever approximately 0. So to prevent that from happening, sometimes you might have to use things like the binomial theorem. And sometimes you might not even be able to use the first term or the second term. You might have to go to the third term where after the first two terms cancel. So that's something to keep in mind. And if the first if the first two terms cancel, you'll often just have to write out a power series. But usually that's not going to be something that you're going to have to do in this class, at least not on the AP exam. So in this case, we are just going to look at the magnitude, so we're no longer going to worry about whether we're in the positive or x direction. We're just going to concentrate on the positive x direction, because that will allow us to understand what happens to at least the magnitude of the electric field as we get really, really far away from the charge distribution. So here we have it, and what we're going to do is this is a very common type of trick to do when you're trying to analyze limiting behavior. You factor out a term from your radical. In this case, we're going to factor out an x squared here. So we factor out an x squared, which means there is no x squared right here. Well, yeah, there is. It's called x squared over x squared. So we're going to factor that out. And what's left is the x squared in the denominator. And x squared to the 3/2 power is called x cubed. And then we can cancel a factor of x here, and we already have a 1 over x squared factor right there. So now that we can say that, okay, when x gets really, really big, we say that d squared over x squared becomes very close to 0. And you might say, well, wait a second, I thought you just said that nothing is ever approximately 0. Well, yeah, nothing is ever approximately 0. But 1 plus something that is very close to 0 is approximately 1. And that's what I have really used in going from this step to this next step. That was the whole point in factoring out the x squared, so that we can end up getting 1 plus a very small term is approximately 1. Now, if it turned out that we had a minus sign here and maybe there was a 2 up here and things ended up getting to 0, we wouldn't be able to do that. In that case, we would have to use the binomial approximation and say that 1 plus a really small term to the 3/2 is equal to 1 plus 3/2 times the really small term. Well, okay, is about equal. That's why it's called the binomial approximation as opposed to the binomial equality. And you can see that in this case, this becomes a 3kq over x squared, which is exactly what we would expect. So again, keep in mind that if this had been a different problem, for example, if I had had a +2 charge at the origin and the two charges above and below were each a -1 charge, then just letting this stuff cancel out here actually would have brought us to 0, and we would have realized, oh, we can't say that that's about 0. We would have had to use the binomial approximation. Actually, we probably would have had to use it twice. So something to keep in mind, especially when we're dealing with dipoles and quadrupoles, which is what we're going to look at next. Some remarks first. When dealing with multiple charges, you should always analyze the situation to make sure that your solution works for the general case, unless they tell you only for the positive x-axis or something like that, or the first quadrant or whatever. So does it work in all directions, and does it work for both positive and negative charges? And also, how does your solution behave at very large and very small distances? Making sure that it makes sense at those very small distances is often very important to at least bug checking, making sure that you didn't make any obvious mistakes. So recall from drawing field lines that lines are continuous curves drawn tangent to the electric field vectors, and the vector at any point is tangent to the field line. The density of field lines is proportional field strength. Field lines never cross, and field lines start from positive charges and end at negative charges. So this is something that we already drew before, except we had it rotated, but here we have a dipole electric field. You have a positive charge and an equal magnitude negative charge divided by an axis of symmetry, and that's how the electric field looks. The question is, when you get far away from this, what does the electric field look like? I'll tell you one thing, it's not 0. It gets very small, but it's not 0. So let's say you go toward the right. Well, as you go farther and farther toward the right, it does get smaller and smaller and smaller. But it's also always pointed down. So if it's pointed down, it's not 0. 0 means it's doesn't have any direction of pointing. So apparently there is some electric field left, even as you get really, really far away. The question is, what is the power law relationship for the electric field as you get farther and farther away? Is it still a 1 over distance squared force law, such as it is with a point charge? Well, let's figure it out. We're going to actually do this example brute force like, and then work the limiting behavior using tricks. So, first of all, let's consider the electric field along the dipole axis, so to speak. And when we say along the dipole axis, we're talking about the axis that goes from the negative charge to the positive charge. As we explored in actually a previous homework problem, the electric dipole vector goes from the negative charge to the positive charge. And something called the dipole moment is equal to the distance between the two charges times the magnitude of each charge. If it's a dipole, then they have equal magnitude, times the unit vector going from one charge to the next. Or you could just say equal to the magnitude of each charge times the vector going from one charge to the next. That's called the dipole moment. And the magnitude of the dipole moment is just the magnitude of each charge times the distance between the charges. So in any case, along the dipole axis is along the direction of the dipole moment. So I'm using these terms right now because they are terms that are occasionally going to come back to us throughout the course. So I figure the more often I use them, the more likely it is you won't forget them. So in any case, let's say that compared with, if you have a dipole with charges at plus or minus d over 2, so consider the origin, and they're on the y-axis, so the plus charge is at plus d over 2, the negative charge is at minus d over 2. If you're above d over 2, then the electric field, the net electric field would be given something like this by the superposition principle. You could call this kind of a free body diagram for electric fields, but instead of force vectors, it's field vectors. So you have a big electric field pointing upward, because you're closer to the positive charge, because we're saying you're above the d over 2, so you're closer to the positive charge that is at d over 2. And a smaller field contribution going downward. Downward because the other charge is negative, smaller because it's at negative d over 2, which means it's farther away from you than the one that's at plus d over 2, because we said that you're located above the charge at plus d over 2. Okay, well, what does the superposition principle tell us? Well, the superposition principle is just a way of rewriting Coulomb's law at making sure that you're adding up your contributions from each charge. Well, the unit vectors are easy. The unit vector for R1 is called J. The unit vector for charge 2 is called J, because each charge is pointing up at toward our point of concern, because we're looking at going farther away. Okay, what are the R's? Well, the distance from your point of concern, which, just going back to the original picture, you might be, say, up here, and the plus charge is at d over 2. So if you're up here, if you're at a distance of y, or at a position of y up here, the distance from y to y equals d over 2 is, well, your coordinate y minus d over 2. Well, what is your distance from your point y to the charge at negative d over 2? Well, it's y minus negative d over 2, which is also called y plus d over 2. So that's how we ended up putting that in here. And in this case, we ended up using an absolute value sign. But I decided to dispense with that because we're assuming that y is greater than d over 2. So all of these distances, there's no way they can be negative without absolute value signs, because y is always greater than d over 2. So r squared is just y minus d over 2 squared for R1, and y plus d over 2 squared for R2. That is the distance from charge 2. So that's what we're looking at right now. What happens when y gets big? So this is where we're going to use the binomial approximation. If you haven't memorized the binomial approximation, you need to memorize it now. The binomial approximation states that if you have something of the form 1 plus or minus a quantity all raised to the n power, that's about equal to 1 plus or minus n times a, if a is much less than 1. So, what does that mean here? Well, first of all, it means that we need to turn these terms in the denominator into terms that can be evaluated using the binomial approximation. So, I need a 1 right here, and I need a 1 right here. So in order to do that, I'm going to factor out the thing that I would like to be 1 that isn't 1. So I'm going to factor out a y. And d over 2 is also called yd over 2y. And so factoring out a y, if you factor it out, you've got to factor it out from everything. Factoring is also called undistributing, so it's got to come from everywhere. So we're still left with this 2y in the denominator of the term that had been d over 2, once we factor out our y. And now this thing right here is in the form of the binomial, where we could use the binomial approximation. So that y ends up getting squared, so we factor that term out, and we're left with this. Okay, well, what can we do with that? Well, something that is raised to a positive power in a denominator is the same thing as putting it in the numerator and raising it to the negative power. So instead of calling it 1 over 1 minus d over 2y or 1 plus d over 2y squared, I'm just going to call it 1 plus or minus d over 2y to the negative 2 power. And the reason I'm doing that is because, well, you can't add together denominators. But you can add together numerators if they have a like denominator, in this case 1. So that's why I wrote it like this. So now I apply the binomial approximation. And since I've already gotten this such that this is just a numerator, after doing that, I can see how things cancel. So the 1 minus d over 2y to the negative 2 power is going to be about equal to 1 minus negative 2 times d over 2y, which is just 1 plus d over y. The 2's cancel. And same thing happens over here. We have a 1 plus d over 2y to the negative 2, which is about 1 minus 2d over 2y, which is just 1 minus d over y. And that works out also. Notice that the 1's cancel. That's nice. And all that's left, we have a minus of a negative, which is a 2dy over 2. We get a factor of 2 up there. And we have a y down here. So we get a 2kqd over y cubed. So, in other words, we see that the electric field for a dipole falls off with 1 over distance cubed, not 1 over distance squared, like it would with a point charge. Now, somebody might wonder, but wait a second, isn't there really just a 1 over distance squared right there? Because this d, that has units of distance, right? Well, here's the thing. Remember, the d is a fixed distance. It's the distance between the charges. Y is an arbitrary distance. As you get farther and farther away, as long as y is much bigger than d, then the electric field can be approximated by this equation, which falls off as 1 over your distance from the dipole cubed. So it's kind of cool. The electric field of a dipole falls off as 1 over distance cubed. Now, you can do the same thing if along the axis that is perpendicular to the dipole axis. In other words, the so-called transverse dipole axis. So in that case, let's say you're along the x-axis. Well, it's like, okay, you're along the x-axis. So in this case, we're going to assume that we are on the positive x-axis. So in that case, the electric, let's say that here's your point that's on the positive x-axis. So let me go back to our situation here. So here's your point on the positive x-axis. Well, the vector going from this charge is going to be an xd, or sorry, it's going to be xi minus d over 2. And the point going from this charge is going to be xi plus d over 2. So it's similar to something that we've dealt with already. And what is the distance between those charges? So here I have it incorrect, so it needs to be fixed. This should actually say square root of x squared plus d over 2 quantity squared. That is square root of x squared plus d squared over 4. So I need that to be fixed. So there is this cool little magical thing that you can do when you're narrating these PowerPoints. You can yell, "Fix it," pause, and it magically ends up getting fixed. So here's where we're at so far. We have our unit vectors, we have our electric field vector with the superposition principle in place, and now we're ready to plug and chug. We know what our charges are as well. So we plug in our charges. There's a minus sign that comes here because I plugged in a negative Q for Q2. I plugged in our unit vectors and also took into account these distances. We got an extra factor of distance down here into the unit vectors, or due to the unit vectors. So we can simplify this because the x components end up canceling. We have an x thing here minus the exact same x thing here, but the y components don't cancel because there was a minus y component in E1 and a minus y component in E2 because we have minus a plus here because of the different charge magnitudes. So this simplifies to this. Now, how do we apply our approximation here? Do we need to use the binomial approximation? In this case, the answer is no, because all we need to do in this case is just factor out that x squared. And when we factor out that x squared, we'll see that we have everything that we need. So when we factor out the x squared, that's x squared quantity to the 3/2, which is x cubed. And there is, we can say, okay, well, when x gets really big, this d squared over 4x squared plus 1 is just approximately 1. And that's all that we're left with, and we're fine. So we have that the electric field at a very large distance along the positive x-axis is negative, and for that matter along the negative x-axis is negative kqd over, well, if it's negative, the absolute value of x cubed. Now, we mentioned dipole moments. After all, this is a dipole. Well, if we want to be a nerd, then we can write this in terms of the dipole moment in an arbitrary situation where here we're assuming that this r is along the axis that is transverse to the dipole, but the electric field vector is given in terms of the dipole moment p vector. If you thought that was a momentum vector, go directly to jail. So negative kp vector divided by r cubed. So that p vector again just being in this case q d j, where where d is the distance between the charges, q is the magnitude of each charge, and j is the vector, the unit vector going from the negative charge to the positive charge. So that is how we can find the approximation of the electric field at large distances from a dipole. There is a similar method used for a quadrupole that is left for the exercises. So a comparison of on-axis versus transverse axis. You might have noticed that there was a factor of 2 that was missing. So the on-axis electric field, in other words, the electric field that's on the axis going from the negative to the positive charge, is twice as strong as that at the same distance on the axis that is transverse. And you can kind of see that from that electric field diagram where the electric field lines are kind of closer together on the axis compared with the same distance on the transverse axis. And also notice there's a negative sign because what you have left after dealing with the symmetry is the field lines from the positive charge going down toward the negative charge in that case. Okay, so in the next video we are going to discuss continuous charge distributions. This is where we are going to break out our calculus, but never fear, because the calculus that you need to do can all be done using integral tables, generally speaking. In particular on the AP exam, you'll be able to use integral tables to evaluate all of those calculus integrals for those of you who haven't yet had a calculus class. So until then, thank you for watching.